Okay, this is the fourth and final video in this series devoted to variations on the Hummer principle. Okay, so what I thought we would do is go ahead and give you kind of a full bird's eye view of what's going on with the performances that use the traditional Hummer principle as well as my variation on the Hummer principle. So in everything we're going to look at today, we will be assuming that one of the actions performed will be a random cutting of the cards. And then from there, a certain number of cards will be flipped face up, followed by another random cut. Okay? Now, there are actually four possibilities here. We could have an even number of cards that we're working with. So parity refers to whether a number is even or odd. So the parity of the packet can be even or it can be odd. The number of cards that are flipped face up can be even or odd. So I've listed all four possibilities here. So we can have an even or odd packet size followed by flipping an even number of cards in each case, or we can have an even or odd number of cards followed by flipping an odd number of cards in each of those cases. Now, the traditional Hummer shuffle is the first one at the top. And if you remember, CATO refers to cut and turn over. And as we'll see in a minute, it's a name that's lacking because it just doesn't give you enough information. And so I'm going to propose a slight modification to that name. I do want to point out that in the case of an odd number of cards in which we flip over an even number and then follow it with a random cut, there's really no parity preservation that I can see. There is one invariance relative to card orientation, namely there will have to be an even number of up-facing cards, and that's something you can check. The third case is the one that I've been showing you in this series. We've been working with an even number of cards, but we've been flipping an odd number of cards, followed by a random cut. Okay? Now, at the beginning, I called this CATO-3 because I had envisioned just turning over 3 cards. Because in the case of the traditional Hummer principle or Hummer shuffle, you flip over 2. And then it was discovered later that you can actually flip over any even number and everything works just fine. Well, the same thing is true for what I'm sharing with you. You can actually flip over any odd number of cards and everything works just fine, okay? And then the final case is where you have an odd number of cards and you're flipping an odd number of cards. And this seems to be the least helpful case because there doesn't seem to be any parity preservation whatsoever of the cards and no regularity to the number of up-facing cards. Okay, so really the only two cases that provide knowable outcomes that could be leveraged in mathematical card magic are the first one, which is just the standard Hummer shuffle, and this new one that I've been showing you in the series. What I've called CATO-3, we start with an even-sized packet of cards. The permissible actions are, of course, cut anywhere, and then follow that up with flipping over the top 3 cards, or any odd number of cards, and setting them back down on top. Okay? Now, let's look at the properties of each of these. So in the case of a random cut, what does it do to the position parity of the cards? Well, it ends up that it preserves it or reverses it, okay? And so why don't we go ahead, so what I've done here, which I think is really going to help, you see under the hood here. Now, the ordering of the values doesn't matter here. The key is I've chosen all red cards, and in particular hearts to work with, which is the same color as the back of the cards. Okay, so that will prove helpful in just a moment. A similar thing here. I've chosen all black cards, namely clubs. And then if you want to picture the backs as black instead of blue, they both start with B. So if you want to think about just the letter B, that would be fine. So I've chosen that so that when these cards are face down, we know that the face of the card is actually a black card. Okay, well, why is that helpful? Well, we're going to go ahead and organize these cards into a cyclic packet, and then we're going to see what kinds of effects our different shuffles and cutting actions have on the cards. Okay, so this is the Klondike Shuffle. It's just putting the red and quote black cards in a alternating relationship relative to each other. Okay, let me just show you that really quickly so you know what we're working with. Okay, so in particular, the quote black cards are in the odd positions, position 1, 3, 5, and so forth, and the red ones are in even positions, 2, 4, 6, 8. Okay, so keep that in mind. So let's go ahead and just see what a random cut does to the organization of this packet. So that's what we're looking at here, this first property. Okay, so I claim that random cutting either preserves or reverses the position parity of all of the cards. Well, it's not too hard to see, because if I happen to cut it right there and move those to the bottom, we haven't changed the position parity of any of the cards. The black cards are still in odd positions, and the red ones are still in even positions. Okay, so that would be a preservation of position parity. Now, of course, if we happen to randomly cut there, let's say, we have reversed the position parity of all of the cards. But the important thing is it still alternates, right? It's an alternating packet, but this time it's had the position parity of all of the cards switched from what they were. So odd positions become even and even become odds. Okay, so that one's not too hard to see, I don't think. Now, the trickier action is this flipping over of an odd number of cards. Well, what does that do to the position parity of the cards? I claim down here that it actually preserves it. It doesn't harm it at all. Okay, so let's begin with this. Why don't I go ahead and just move that down so that we always have kind of a same starting packet. So we have the blacks in the odd positions and the reds in the even. Okay, so what I'm claiming then is if we were to push off the top 3, flip them, it will not change the position parity of the cards. Now, it is changing the position of some of the cards. In fact, in particular, this 9 of clubs and 7 of clubs are going to be moved from either position 3 to position 1 or position 1 to position 3, right? If we flip those over. But the 9 of hearts, which is in the second position here, it doesn't go anywhere. It's still in the second position even. But more importantly, it's still in an even position value. Okay? So flipping over 3 has no effect on the position parity of all of the cards. And that's important too. It hasn't affected any of the cards. Okay, let's just really clarify that. Okay, so remember this was black, or think of it, blue on the back, okay? And we know that it started in an odd position, namely it was over here. So we still have, quote, the black cards in the odd positions, so 1, 3, 5, 7, 9, and so forth. And the even, what started out in the even positions, are still there. This 9, which had a red back, is in position 2. That's where it started. And then the next red is in position 4, which is even, and so forth. Okay? So flipping over 3 does not affect the position parity of any of the cards. Okay? Now, of course, just flipping one card, 1 is an odd number, so we were allowing the flipping of just one card, since 1 is odd. That doesn't change the position parity of this card. It does change its orientation, right, from face up to face down or vice versa, but it doesn't change the position parity, okay? And then if we do a random cut, what have we done? Well, in this case, we've actually reversed the position parity of all of the cards again, right? Remember, we had a black on top, meaning the black cards were in odd positions, But now it's the red cards that are in odd positions and the black cards are in even positions, okay? So for what we're going to do, that is perfectly acceptable. That will not undermine anything that we hope to accomplish, okay? Now, what if we push off and flip 5 cards? Five cards. Five's odd, of course. Well, what you have to do is you just have to look at the symmetry of what's going on here. Okay, so let's just focus on the 5 cards here. Is there a symmetric quality to the color distribution of these cards? Well, there certainly is, because on the outer edge we have, quote, red cards. Come in one, we have, quote, black, let's say, black cards. And then in the very center, we have a red, okay? Now, if this is flipped over, it has the exact same effect as the packet of 3, okay? So we won't actually be changing the position parity of any of the cards, even though cards are changing, or at least most of them here, are changing position, but not position parity. So the outer ones are still, quote, red. You come in, these are black. And the middle one's red, which is not going to go anywhere, right, in terms of where it was. Okay, so flipping over 5 cards will not change the position parity of any of the cards, okay? And then you can do a random cut and so forth. Now, I did have a kind of a qualifying statement where if at the very end, let's say you're setting these down on the table. Do you remember we also did a mixing on the table where the spectator was allowed to leave or flip, okay, that kind of thing. Leave or flip. Here's 5. Maybe they'll leave them. See 3, flip. Maybe flip those. Okay. Now we've got down to 4 cards. Okay. Now the safest thing to do is go ahead and either flip one, set one of these down because 1 is odd, and then it leaves you with an odd number. Okay, which you can flip down either way. Okay. But if you choose to, or let's say in the end, just because of the number of cards, I'm going to just set those down. Okay, so what I'm showing you is if you happen to finish with an even number of cards, in particular 2, if you would like to set these down, you can do that. But you must flip that even size packet. Okay. Oh, it's because I set these down wrong. Okay. Sorry about that. See, I needed to flip that one as well. Okay. And so for this to work, you'll actually, and you can test this, if you put them down like this, you're going to have a problem, like I just did a moment ago, where you have 2 even position cards next to each other. You've destroyed the position parity, or you have not preserved the position parity of all of the cards. So if you're wanting to set down an even number of cards, you must flip that one. And the key is to just go ahead and do it. Don't make a big deal of it. Don't ask the spectator, even draw attention to it. But once again, I think the safest thing to do is go ahead and always work with an odd number. Okay, so we've kind of mixed these, quite well here. Maybe we'll just do 3, 4, 5. Flip those, and these go down as is. We're back to this situation here, so maybe we'll go like that, and then go like that. Okay, so now since this action of cutting either preserves or reverses the position parity of all of the cards, and this flipping over of an odd number of cards preserves the position parity, what that means then is you can separate these into the original even position cards and the original odd position cards. And that was kind of the key step. So the simplest way of doing that is to do just a left-right. You remember that? We showed you more sophisticated ways of performing this action of like pulling apart the even position cards from the odd position cards, kind of pulling those apart. And so these will all be, quote, black, right? These will all be cards that I believe originally started in odd positions in that beginning packet. And these are all cards that began in even positions within the packet. Okay, so that's kind of what's going on with this flipping over of an odd number of cards. Essentially, because of the symmetry of that packet, like red, black, red, it doesn't matter if you switch it. It's still going to have that red, black, red position parity distribution there. Okay, now I do point out down here that to my knowledge, I don't know of any invariance for this CATO-3 or CATO-Odd principle that I've shown you when it comes to the face-up, face-down orientation of the cards. Okay, now that's a little bit different from the traditional CATO or traditional Hummer shuffle, which we'll show you at the end, just to kind of show the contrast. Okay, and then here I have a bold suggestion. Over the years, several prominent card experts have recommended various name changes to this cut and turn over CATO principle. Okay, and within the procedure used here, we're assuming that we have an even number of cards, as we saw at the very beginning. So remember, we're looking at an even number of cards, but we're flipping over an even number of cards. So to draw a distinction between that and what I'm showing you now, my suggestion is that we rename the traditional Hummer procedure, or CATO procedure, to CATO-Even. And then we can refer to this new principle as CATO-Odd. Okay, so that would draw a clear distinction between the two, reminding you what's the parity of the number of cards that are being flipped face up along with random cuts. Well, for the Hummer shuffle, it's an even number of cards that are flipped face up. For this CATO-Odd, it's an odd number. Okay, so I don't know if that's going to stick in the magical or mathematical communities, but I think that would be a good name change or modification to the name to kind of draw a distinction between these. Now, I'll be honest that to my mind, the CATO-Even, which is the traditional Hummer shuffle and principle, is the more powerful principle. But the one that I'm showing you, CATO-Odd, I don't think is too far behind, since it has an invariance that the CATO-Even principle lacks, since this CATO-Odd actually preserves or reverses the position parity of all of the cards. Now, that does not happen with the traditional Hummer shuffle. Okay, so I want to kind of show you that to kind of finish up here. And this will actually help you understand the Hummer principle a little bit better as well, actually. So what we're going to do is that using this alternating, red, black packet here, it really does make much clearer what's happening with the cards. It really, really does. And so you can kind of see under the hood by using a packet structure such as this one here. Okay, and why don't we go ahead and we'll just have the blacks in odd positions again, and the reds in even positions. Okay, so I'm going to take just a moment to draw a distinction between what I've been using in this series versus the traditional Hummer shuffle. Okay, so there you would need an even number of cards always, and which we have. Okay, so what is a Hummer shuffle? Well, this is where you randomly cut, flip the top two, randomly cut, flip the top two. Now it ends up you can flip any even number actually. So you could actually flip 4, random cut, flip 4 maybe again, or 6 or 8. Whoops, sorry about that. Random cut, we'll maybe flip 4 again, and then we'll do one more and we'll flip 2, let's say. Random cut, flip 2. Okay, so what invariants or what properties survive all of that? Is there anything interesting about the packet? Because that's quite a bit of, mixing and moving around of the cards. Well, one thing you'll see right off is it does not preserve the position parity of the cards at all, right? So like here's a red card means it was originally in an even position within the starting packet, right? So we have this even, odd, odd. So these two were not in opposite positions relative to parity. These are both odd position parity. Okay, so the position parity of the cards has been destroyed. The same thing here. We have two cards that started out in even positions. Now they're next to each other. Okay, and in particular, that means we know nothing about the position parity of the cards now versus what they were at the beginning. So that information is gone. It's destroyed. But in the case of what I've been showing you, we actually preserve this, right? The position parity of the cards either is preserved or reversed. Okay, so we kind of know where cards are after all that mixing, and we can separate the original even position cards from the original odd position cards. Okay, well, you might wonder, well, what's the Hummer principle for if it destroys the ordering of the cards? Well, its invariance is far more subtle, but powerful. I mean, that's why it's a principle that has survived for 80 years now. Okay, so one of the invariants I'll go ahead and point out is that the number of up-facing cards in even positions, now we're relabeling these, like this is card 1, 2, 3, 4. We're giving new position parities to the cards as they are now, right? So the number of up-facing cards in even positions will be the same as the number of up-facing cards in odd positions. Okay, kind of a curious thing that's being preserved. So let's take a look. So this is an odd position card. It's the first card. Okay, so here's one up-facing card in an odd position. So we have one. Okay, no, one more. So 2, 3, 4, no, 5. So we have 5 up-facing cards in odd positions. Now, what about in even positions? Okay, so this is position 2 here, which is even. So we have 1, and then no, 2, 3, 4, no, 5. We also have 5 up-facing cards in even positions as claims. Okay, so that is one invariance that you can plan on the packet having. So in particular, what that means then is if you were to separate these into a left and right pile by way of a left-right shuffle, those two halves will have the same number of up-facing cards. Okay, that's one property of the Hummer shuffle. Okay. Now the other one is far more difficult to detect. Okay. And I've given a whole series on the Hummer principle, trying to truly look under the hood there to see what's going on. But the other invariance, which is absolutely amazing, is if I take these cards and perform something called a parity separation procedure, something remarkable happens. Okay, so what is a parity separation procedure? Well, the simplest of all of them is simply a left-right dealing in which you flip over every other card. So if you do like down, flip, 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 down, flip. Okay. Take a look at what we've done. Look at this. We have red cards facing up, which were originally in even positions. The same thing here. Okay, so if we just kind of randomly stack these, what you'll find is all of the cards that started out in even positions at the very start are facing up, let's say, and then all of the cards that started in odd positions are all facing, quote, down, right? I flipped over the packet to show you that, okay? So that's called a parity separation procedure, and it reveals one of the underlying properties of this packet that is preserved through as many Hummer shuffles as you're willing to put it through. Okay, so just to finish up here, one thing I thought of recommending to all of you is if you're interested in kind of really seeing what's going on, with this new principle, well, with the Hummer principle as well, but the new principle that I've been showing you in this series, what you could do, and it would be most illuminating actually, is create a packet such as this one here at the very start, and then just step through the routines that I've shown you. So I have videos that show you 3 very different routines using this CATO-Odd principle, as I'm calling it now. Okay, so start with something like this, and then just follow the procedures that I show there. Okay, so for example, when I'm mixing them, supposedly, before we start, do you remember? Like we said, well, we all saw the cards. Let's go ahead and just mix these up, and so that no one knows where anything is. Well, we know where things are, right? If you're kind of using X-ray vision to see what's going on. And then we randomly stack these. And then I said something like, well, let's follow that up with a Klondike shuffle. Okay. Well, that just puts it back in an alternating relationship, which is where we need the packet for our CATO-Odd routines. Okay. So this gives the illusion of kind of mixing the cards when in fact it is not. Okay. And then you go through and, do the random cut, flip an odd number, and it's not going to change. It's not going to destroy the alternating nature of the packet. Okay. So it's either going to preserve or reverse the position parity of all of the cards. Okay. So we know that now. Okay. And then one of the ways that we separated them, if you remember, we at the very end to kind of separate the even positions. Now the spectator doesn't know this, that we're pulling out the cards that we secretly put in even positions at the start from the cards that we put in odd positions. But if you remember, we also did this dealing out into 4 piles. Remember that? Okay. Well, with the colors here helping us, you can clearly see what's going on, right? Okay, and if you remember, we took pile 1, we stacked it on top of pile 3, and then we took pile 2 and put it on top of pile 4, okay? Well, what have we done? We've just separated cards that were originally in, let's say, odd positions in this beginning packet, from those that were in even positions. Okay, so if you construct this packet that I've shown you today and then just on your own follow all of the mechanics of what I've done in these 3 routines, you'll clearly see structures being converted from one to another, or being preserved, or you'll see that the parity of the cards has not been changed at all, or maybe it's been reversed. Okay. So anyway, I hope this series has been of interest to you. And once again, here's a full look at all of the possibilities for what we're doing with this random cutting followed by flipping either an even number of cards in the case of the Hummer shuffle, or an odd number of cards, which I have been doing in this series. So thank you for watching, and take a look at my series devoted to the Hummer principle, because boy, is that a powerful principle. And I believe I have 8 videos in that series that goes very deeply into the Hummer principle that will spark your interest and get you thinking about creative ideas in the realm of mathematical card magic. So thank you again.